record, it's like the class never even happened. All right, now we got everybody. So welcome back. Happy Tuesday. Happy garbage day, I should say. I felt like I should say have a good weekend already, like it's Thursday, but no, it's Tuesday. It's Tuesday all day. We have one more week after this one before spring break, though, so that's nice. We got a little bit of a reprieve. Even if your spring break is just, catching up on laundry, right? That's still something. Yeah, so as I was saying before, homework 2, all the grades have been updated, so you should be able to log in and see how you did. I can't talk about it as a class yet because not everyone has finished, but if you have questions about why something was incorrect or what you should have done, you can send those to me individually, office hours, email, and if needed, we can schedule individual meetings as well. Let's see, let me get this screen share going so that we can all be looking at the same thing. Where we had left off last time was talking about how to put grouping variables into a model. So when you have categorical predictors of a quantitative outcome where they have more than 2 categories, then we can't just put them in as is, and we got to do something else instead. So what do you remember from last time? I've got a contextual clue here with some code, but what do you remember? More than 3 categories? What happens if you have more than 3 categories? 3 or more categories, I would say. Yeah, we got to make new predictors that are each 0 or 1. And how many new predictors do we need? Like if I have a categorical predictor that has 3 categories, how many new predictors do I need to represent those 3 categories? It's 2? Yeah, this is a finger question. I don't know if there's Zoom reactions that have numbers in them or not. But. And if I had 4 categories, how many new predictors would I need? 3. And if I had 5, I would need 4. Yeah. So the reason it's always number of categories minus 1 is because the model already has an intercept. So when all is said and done, you would have as many fixed effects as you have categories to be represented. That will make it so that each category gets its own outcome mean, and you can test all possible mean differences between pairs of categories. So we had an example then, this little table right here. I am on page 3 of example 3. This is the same general social survey data set from 2012 that I'm working with the subset of. And I'm looking at a question of self-reported working class as a predictor of annual income. So people could choose whether they rated themselves as a lower class, middle class, or upper class. And this little table here summarizes the frequencies in each category, as well as the 2 new variables that I need to create. So each of my variables is going to distinguish one of these categories from the other. And I need to decide which of my groups I want to be the reference as the first step. So in your homework, for instance, when you start homework 3, I will give you instructions as to which group should be considered the reference. And what that should mean to you is make that group the 0 across all of your new categories. So the reference group has their predicted outcome given by the intercept only. And each of the new predictor variables then describes how an alternative group differs from the reference group. So how the 1 group differs from the 0 group in each of these. So this table is what we're trying to do. We're trying to make 2 new columns out of this original categorical variable that's 1, 2, or 3. And each of the new columns has a 1 in only one of the places. So I think we went through the code last time. Would that be helpful to go back over again? Yeah, the code is always the tricky part. Understanding the concepts is one thing, but then actually implementing the concepts in software is another. So the end result of what I'm trying to do is create this little table right here. That's the goal. So first up in SAS, Note that all data transformations have to happen inside these two sets of statements. So in SAS, you can have more than one data set open at a time. Therefore, you must tell it which data set you're trying to do things to. So when you list the same data set in both places on data and work, or set and data, work is the place where these are, then you are essentially saving it as itself. All right, do we have questions? No? Alrighty then. There's my mouse. I lost my mouse here. So first step is making two new empty variables. So that's what it looks like in SAS. This is what that step looks like in Stata. So see if I can get everything on the same page here highlighted. And this is what it looks like in R. So the sections of code that I have highlighted right now are all doing the same thing. They're taking two new variables and filling them with blanks. That way they only get recoded into zeros and ones if they meet the conditions that I specify. So then the first is, what do I want to happen if you're in group 1? So if you answered that you're lower class, then I want both of your new predictor variables to be set to 0. So that happens there in SAS, that happens there in Stata, and it happens down here in R. So the tricky part with these sorts of statements is figuring out where the new variables go and where the old variables go. And if you accidentally write over one of your old variables, no worries, just re-import your data by running your program from the top again, and you'll get your original data set back. So if work class equals 1, work class is the original column that I have as 1, 2, 3s. So it shows up right after the if in SAS, it shows up after the if at the end of the command in Stata, and it shows up inside the which, inside the brackets in R. So work class is the original variable in this example. The two new variables to be created, I have named L versus M and L versus U because that's what they're going to represent. They're going to tell me the difference of the low versus the middle group and the low versus the upper group. So if work class equals 1, those two new variables are both 0. Okay, how are we doing so far? We got a question. Under what circumstances does it overwrite the data? It happened to me while doing homework, but I did not know why, and I had to re-import the data again. So you can overwrite your data if you create a new variable that has the same name as an existing variable. It doesn't understand that you're trying to make a new one if you name it the same thing. So if I tried to say, you know, work class equals dot or something up here instead, then I would be emptying that column. And if that ever happens to you, all you have to do to solve it is run your program from the top again, and it will re-import your data. So there's really no harm to it, and it will happen to you at some point. It happens to everybody, myself included. Okay. So then second group, if work class equals 2, right here, and I'm going to get off the page for R, but the 2 right there are for that one. So if I'm talking about work class equals 2, the first variable takes a 1, and the second variable stays at 0. So that happens 1, 0 here, 1, 0 in Stata, and then 1, 0 in R. And then last but not least, if work class equals 3, then the second variable takes a 1 instead, and that happens there in SAS, that happens there in Stata, and it happens down here in R. Okay. So now when I go to do my analysis, I do not need and should not refer to work class anymore. I have functionally replaced the representation of that variable is 1, 2, 3 with my 2 new predictors that are coded 0 and 1. So work class is done. All right. Any questions on this part? Now, in your homework that is not yet available, because I haven't made it available yet, you'll get to do this for 4 groups. So just a little bit of an extra challenge. And what did we say at the beginning of class? If I had 4 groups, how many new variables would I need to make? 3. So you'll have another set of these commands where I would have a 3rd variable in here for SAS. I would have a 3rd row for each of these in Stata, and a 3rd row for each of these in R. So I have a 4-group example in the slides after this to show you the logic, but it's not any different than this sort of patterning. But 3 for now. We'll start with 3. And this type of 0-1 coding is called dummy coding as a general rule. The specific type of dummy coding that I'm doing here is indicator coding. That's a term that's used in your textbooks, so I'm trying to be consistent with how they describe things. All right. So then the logic of how the model is going to tell us what the predicted outcome is for each different category of the predictor, as well as what the differences are between the categories. The model will tell us all of those things at the same time, if we know how to ask. So here's my model. This, by the way, this is a general linear model like the rest of the class is about. Do you remember the special name for this? This type of model where you have a categorical predictor of 3 or more categories of a quantitative outcome has a special name. You may see this name used in publications. It starts with an A. ANOVA. Yes, this is what's known as a one-way analysis of variance, or ANOVA for short. So I have 3 fixed effects, meaning 3 betas. Beta 0 is my intercept. My intercept is always the same thing, the expected outcome when all my predictors are 0. Beta 1 is a slope. That's going to describe how the M group differs from the L group, middle and low. And beta 2 is also a slope. That's going to tell me how the upper group differs from the low group. So then the prediction for each type of person is given by y hat here. So the E drops off if I'm talking about a predicted outcome. And these 3 terms are what I need to figure out how the model says what the outcome's supposed to be for someone in any category. So then the low group. This is how we figure out how the model tells us the mean for the low group. The low group is my reference group, meaning they are when the new predictors that I created are both 0, which means their predicted outcome is given by the intercept only. So beta 0 is the mean for the reference group, the low group in this example. The mean for the other groups is created by setting the values of my new predictors to the 0s or 1s that correspond exactly to my coding scheme. So that should be internally consistent with respect to how you made the variables, what values would go in each of these places. So the mean for the middle group works out to be beta 0 plus beta 1, and the mean for the upper group works out to be beta 0 plus beta 2. All right, how are we doing? Okay so far? Okay. So if the model tells us how to get the mean for each group, then it has to tell us how they differ also, because a difference is obtained via subtraction. So low versus middle. If I'm treating low as my point of, like my UR here, this is my reference, and I want to know how middle differs from low, then I take what the model says the mean is for middle, and I subtract from it what the model says the mean is for low. and I'm left with just beta 1. So the interpretation of beta 1 is directly how the middle group differs from low. That's how we set it up in our coding scheme. Likewise, the mean for the upper group is beta 0 plus beta 2. If I want to know how the upper group differs from the low group as a comparison, the low group is given by beta 0 only. So beta 2 directly tells me how the upper group differs from the lower group. So as a general concept in setting up these predictor variables and how they work in a model, under this kind of dummy coding scheme, indicator coding, where you set one group as the reference and then each group is relative to that, everything in your model is going to tell you about the reference group. Beta 0 is going to tell you the reference group mean. The slopes are all going to tell you how each other group differs from the reference. To get to any kind of information about not the reference group, it's going to be a linear combination. So to get to the mean for the middle group, it's 2 betas added together. To get to the mean for the upper group, it's these 2 betas added together. And then likewise, if I know what the mean is for upper, and I want to compare that to the mean for middle, then the beta 0s drop out, and I'm left with beta 2 minus beta 1 as how the model tells me how the upper group differs from the middle group. So there's 6 things we want to know. The model gives us 3 out of the 6 directly, and the other 3 are linear combinations. So fixed effects are already given to you in your model output. You don't have to do anything. They show up. Anything that I have marked as a linear combination, we have to ask for additionally. Okay, how is the logic sitting with everyone? Is this okay so far? At least in theory? We never know if it's really okay until you sit down to do it, right? It's like you can be like, oh, that makes sense. I think I'm following. And then it's like you open up R and it's like, ah, what do I do now? So it's in theory. We're working with theory here. Practice is coming. So then let's get some numbers on this. So in SAS, to start with, I'm within Proc GLM. So we're pretty much going to stay within Proc GLM for the rest of the semester. I have to tell it what the name of my data set is. So this is the first thing that you would have to change if you're using this example for your homework. You tell it that it's for homework 3, not example 3. And then you have to tell it what variables you want in your model and in what places. Income is the outcome that I'm predicting. Equals then delineates what the predictors are to be. So note that it's my 2 dummy-coded predictors of L versus M and L versus U that go here, not work class. Work class is gone. Likewise, in Stata, it's the command regress. The first word after regress is the outcome variable column name. And then after that are predictors, each of which has C dot in front of it. C dot is used in Stata to delineate a predictor that is being treated as a quantitative variable. If you don't include C dot, it's fine. But in some instances, I've gotten error messages in subsequent commands that I use to get linear combinations without the C dot. So to be on the safe side, I always put C dot in front of any predictor that is to be treated as quantitative. The alternative in Stata, by the way, is something called I dot, and I am deliberately not showing it to you. So it does exist. You may see it in other instances. But what I am teaching you is the underlying logic of how I dot works, doing this dummy manual dummy coding process. Is that way you'll know exactly how to set up the model to get anything you want out of it. And then the analogous command in R is LM. That stands for linear model. It wants to know what data set you're using. So again, if you're adapting this code for your homework, it would be homework 3 instead of example 3. Formula is like model. Formula equals then tells what the equation for the model is supposed to be. So right after the equals is where your outcome variable column name goes. Squiggle then means what is it going to be predicted by. The 1 is used to represent the fixed intercept. I keep it there so that I don't forget about it with the rest of my coding. And then the 2 new predictor variables. So 3 fixed effects going into the model. The ANOVA option prints residual variance, which is the first thing that I ask about to see if you've got your model correct in homework. And it's also a useful summary of what happened with respect to your prediction. Summary then actually prints your results, and confidence intervals then are obtained with this confit option right here. So it takes all 4 lines to get to the same output that is included by default in the model statement of SAS or the regress command of Stata. Okay. Should we look at output for just that much? Just fit the model, see what happens? The rest of the code then will make sense later. So this is the table that up till now I had said you can ignore it. Starting in this unit, we don't get to ignore it anymore. But I haven't explained what it is, so I'm going to skip it for just right now, and then we'll talk about what it means in just a minute. What I want to get to is this table of parameter estimates. This is SAS Output. And let's see here. Yeah, I don't have the output from the other programs it looks like in here because it looks almost exactly the same. So the default table that you get that tells you what the best answer is from your data for each of the fixed effects is right here. That's what I want to focus on for right now. Okay, so first thing here, intercept estimate is 13. That is what the algorithm decided the best answer for beta 0 fixed intercept is in my sample. It's 13.65. Now ask yourself, what's an intercept? This is one of those definitions you want to have committed to memory. What's an intercept? Is anyone feeling brave? Want to tell us what an intercept is? Or type it, as it were.
The mean when x is 0.
The mean when x is 0. Yeah, I would say the conditional mean, or you could also say the predicted outcome when x is 0. Either of those work. Yep. So given that it's the mean when x is 0, for whom is this the predicted outcome? Which category are we talking about if all the predictors that we made are 0? Yeah, the low group. The lower class group is the 3.
What did you call them? You call them?
Yeah, you can call them the low group as opposed to the middle group or the upper group. Lower class is the designation in the survey. That's what they called it anyway. Not a value judgment, just a variable. So yeah, 13.65 is the expected annual income for somebody who labeled themselves in the lower group. That's what I just learned. If I go to the next column over, 0.62 is the standard error for that. So that tells me the expected inconsistency of that predicted outcome across repeated samples on average. The rest of it is typically not of interest for an intercept because it's a predicted outcome and not a relationship. The other 2 rows describe relationships. They're slopes. So beta 1 is given by this row. The estimate is 8.85. That is not a predicted outcome. That is a slope. So what's a slope? This is another one we got to have committed to memory. Ask yourself, what's a slope? The relationship between what? Low versus middle here, yes, but more generally. Like if you didn't know what the variables were.
The change in Y unit.
Yeah, the change in Y per unit change in X. So the change in annual income for a 1 unit change in X in this variable means moving from the low group to the middle group. So putting that all together, income is predicted to be higher because this is a positive slope. So as X goes up, Y goes up. That's what positive slope means. Income is predicted to be higher by $8.85 thousand for people who put themselves in the middle group instead of the low group.
So here, for someone in the medium category, it will be the 13 initial plus.
For someone in the middle category, what?
It will be 13 plus 8.
Exactly.
Whatever X is.
Yep, so somebody in the middle category, their predicted outcome starts with 13 for the low group, and then how it differs in the middle group is 8.8, and you add those together and 12-ish, whatever it works out to be. That's their predicted outcome for the middle group. Exactly right.
Plus any residual.
Plus residual, yeah, we're talking predicted. Yeah, so these are not going to be exactly right for any one person, but on average, this is what the model says is supposed to happen. So this is a positive slope. Is it significantly positive or non-significantly positive? Yeah, where do I need to look? Yeah, I got to drive over past standard error, past t, until I get to this magical column right here. That's my p-value. A p-value, another definition to have committed to memory, is the probability of finding a result that extreme or more extreme if the null hypothesis is true. In this context, if the true slope in the population were 0, if there were no difference in income between people who put themselves into the middle versus low categories, how often would I see a slope of 8? Less than 1% of the, less than 0.01% of the time. Very, very unlikely. The t-value helps quantify how unlikely, given that p is 0 to the 4th decimal place. A slope of 8 is 8.8 standard errors away from the null hypothesis. Way into unexpected territory if the true slope were 0. So putting that all together, the slope is positive. The slope is significantly positive, meaning that people who put themselves into the middle group make significantly more money than people who put themselves into the lower group. The standard error that we skipped over here, this is the standard error of that slope specifically. Standard error is how far off on average the sample whatever is from the population whatever. So in this context, it is the standard error for the slope characterizing the difference of how middle compares to low. So on average, that slope is going to be off from the population slope by 1. Expected inconsistency of 1, plus or minus 1 on average is a standard error. Okay, how are we doing? Okay enough? Okay, so up to this point, we would have done what you did at the end of your last homework or the end of the last unit with one binary predictor. So there's nothing different about the story if we add the second. Same exact everything, swapping out upper instead of middle. So 10 is my slope. 10 is a positive number. That means people in the group coded 1 are higher on their outcome than people in the group coded 0. In this story, people who are put themselves into upper class as the 1 for my predictor are higher on average by 10.98 than people who put themselves into the low group as the 0. If the true slope were 0, How often would I find a slope as big as 11? Less than 0.03% of the time. So how do I know if this p-value is significant or not? What's my cutoff? Where does the dividing line of significant start? Yeah. 0.05 is the convention. So what I'm asking basically is alpha is your dividing line, and that's something you're supposed to set ahead of time before you even collect your data. That's one of those things I have to decide on how often I'm willing to be wrong. Alpha is your type 1 error rate. 5% of the time, even if the true slope were 0, you get a slope this extreme. You're willing to be wrong 5% of the time. So in your homeworks, I will tell you what your alpha level should be. It's almost always going to be 0.05 for simplicity, but that's a decision that you make. So this is definitely under 0.05. So this slope is also significantly positive. However, standard error for it is much bigger. Now here's a question. Why is this standard error about 1, but this standard error is about 3? Any idea why they'd be so different, even though they're characterizing the same type of thing? Because which one? Yeah, because, yep. Bigger variation in higher incomes. Good guess, but this model assumes that the variation is actually the same across incomes. That's a testable hypothesis. The reason why that standard error is so much bigger boils down to power or lack thereof. There's only 20 people who labeled themselves upper. Yeah, so the model is less certain what the mean should be for 20 people than what the mean should be for 300 people. So we have less power to say anything about the upper group because they're so much smaller. We have a lot more uncertainty in what the slope is that differentiates those 20 people from the low group that has, 400 and some odd people. So this, even though the slope numerically is bigger than the other one, the slope of 10.98 is numerically bigger than 8.85. In terms of setting them on a standard of comparison, the t-value is much bigger for the smaller slope because the smaller slope is more consistent. So t is the equalizer here. T tells you how many standard errors away from the null hypothesis your slope is. So we have a much bigger t for the slope that's numerically smaller because it's more consistent across repeated samples. Okay. Questions or any of that you want me to repeat? Okay, so let's do some math in our heads. If I want to know what the model says the predicted outcome is for the intercept, I don't have to do any math. The low group is the intercept, it's right here. Will I repeat the role of t one more time? Certainly. T is an equalizer. It's a standardization. It's a way of expressing in standardized units how far away your sample slope is from the null hypothesis slope. Null hypothesis is 0. So a t of 8.82 tells me that this slope is 8.8 standard errors away from the null. And this t tells us that the second slope is 3.67 standard errors away from the null. So the second slope is closer in terms of expected versus unexpected, because it's noisier. We're less certain what the second slope is going to be in any one sample. It has a higher standard error, a higher inconsistency. Okay, does that help? Yes, okay, cool. Okay, so where I was going. If I want to know what the mean is for the low group, do I have to do math or use my eyeballs? We'll stick with yes or no questions here. If I want to know what the mean is for the low group, can I just stare at this and find out, or do I have to think? Thumbs up for stare, thumbs down for think. Stare, yeah, the mean for the low group is that one. How do I know that? Because I coded the low group 0 in both of my predictors, and the intercept always gives me the prediction for the 0 group. If I want to know what the mean is predicted to be for the middle group, do I have to use my brain? Boo, or just stare? Meaning, does the number show up here for what the mean is for the middle group directly? Yeah, in this case, it's not this one. That tells me the mean difference.
Just a small amount.
Yeah, so this one I got to add. The mean for the middle group is those two put together. The 8.8 is not the mean for the middle group. It is how the middle group differs from low. 8.8 is a slope. So this is a very common point of confusion that I want to hit really hard so that it's hopefully less confusing. This is not the mean for the middle group. This is how the mean for the middle group differs from the mean for the low group. So to get to what the mean is for the middle group, I got to add these two together. 13 plus 8 is what the middle group's mean is. Likewise, if I want to get to the mean of the upper group, the mean of the upper group is not 10. That's how the upper group differs from the lower group based on my coding scheme. What do I need to add together to get to the mean for the upper group? Yeah, 13 plus 10, exactly. Now I can do that math in my head, but getting a standard error for it is much harder. So we're going to make the programs do the math for us. And while we're at it, is the comparison of middle versus upper given to me directly by any of these numbers? Is the comparison of middle versus upper given to us directly by any of these numbers? It is not. But I know that if the middle group is different by 8.8 and the upper group is different by 10.98, I can subtract the two and figure that out. Yeah, subtract middle from upper. But I might want to know not only what is the difference, but is that difference also significant? And I need a standard error for that. So that's the rest of the code that I skipped over, is getting these additional quantities that the model tells us about indirectly as linear combinations of the fixed effects. So I asked for all 6 things using the same set of codes to help you understand how the codes work, even though I only needed 3 out of the 6. So I'm actually going to start with Stata, because Stata is the most transparent. So the Stata code for this model, I'm talking about this little section right here. Each of these is a linear combination of the model fixed effects, where the fixed intercept is underscore CONS. That is what beta 0 is going to become. This variable for L versus M, that is what beta 1 is going to become. And the variable for L versus U is what beta 2 is going to become. So then the times 1 or times 0 is telling it for that group, how are those variables coded? It goes directly with this logic right here. If I want the predicted outcome for the low group, then I set both of my variables to 0. If I want it for the middle group, this one turns to a 1. If I want it for the upper group, this one turns to a 1. That same pattern is in these 3 statements. So the first one I don't need. That's there for pedagogical purposes because the first one kills both of those terms. But the other two, this is going to do the math for me of the 13 plus 8 and the 13 plus 10. So then the differences are the next three. And the way that you can figure these out is by starting with these lines and literally doing the subtraction of the code. So if I start with middle right here, and I subtract the values that go into the low statement that's right before it, this constant minus a constant drops. L versus M of 1 minus L versus M of 0, I keep a 1, and these two stay 0. So L versus M is given to me by just the first term. Likewise, if I start with this line and subtract the low line from it, the only term that I keep is right here. And then the last one is the one that is not given directly by a model parameter. Upper minus middle. So if I keep this one on highlight. So constant of 1 minus constant of 1, that drops. L versus M of 0 minus L versus M of 1, that gives me the minus 1 down here. 0 minus 1 is minus 1. 1 here minus 0 here gives me the 1. And so that line is beta 2 minus beta 1 when all is said and done. That gives me the difference for the non-reference groups. So I like that Stata has the plus signs in here and the multiplication signs in here because it makes it more explicit what is actually happening. So the numbers that go here are the values that correspond to the variables. The variables themselves correspond to the betas to be estimated by the model. So the only lines I really needed to write are those two and this one. The other three are given directly already. But I wanted you to have all 6 so you could see the pattern. Okay. Questions on that, or anything you want me to repeat? You will get a chance to practice this in your next homework. You want to see the SAS code? Why not? So in SAS, the pluses are not here, and the multiplication signs are not here. But otherwise, it's pretty much the same. Beta 0 is referred to by the word intercept. I need one of those in each predicted outcome. L versus M stands in for beta 1. If I'm predicting an outcome for the low group, that's when these are both 0. If I'm predicting an outcome for the middle group, it's 1, 0. If I'm predicting an outcome for the upper group, it's 0, 1. And then the differences between them. The difference of low versus middle is directly given by that parameter alone. Low versus upper directly is that one. And then the difference of those two, the comparison is minus 1 and the alternative is 1. Because it's 0 minus 1 is why it's minus 1 there. So that's beta 2 minus beta 1, according to SAS. Okay. You ready to see R? Am I frozen? You guys are frozen. Everyone's frozen in front of me. Nope, now we're back. Are we okay now? Good. Okay, you ready to see R? All I can tell you, for those of you who are trying to learn R, I'm sorry. It's not my fault. It sucks, but this is how you do it. It's a series of values that are the multipliers. That's all you list. So the order of these things corresponds to the order of your fixed effects right here. And that is why I always put the 1 in here, is to remind myself not to forget that one. So the 1 is for the fixed intercept. This is going to give us beta 1. This is going to give us beta 2. So within this GLHT statement, it wants to know what model results to pull from. So this is my model class that I ran up here and saved the results to as an object. I'm binding together multiple rows to create multiple statements. So the 1 in the first column here, that corresponds to, I need 1 beta 0, please. Because at a minimum, a predicted outcome is created by the intercept for everybody. The second column is what is the coding for that group with respect to L versus M. Well, if I want the prediction for the low group, it's 0. If I want the prediction for the middle group, it's 1. And the prediction for the upper group is also 0. Then the last place is what is the value of the predictor variable that corresponds to L versus U. And it's only 1 if I'm talking about the upper group. So the values are the multipliers that show up with the asterisks in Stata, or that are just the straight values listed in the code in SAS. And then the differences, if I take this row right here of coefficients and subtract from it the first row, I get this result. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. If I take middle and upper, 1 minus 1 is 0. 0 minus 1 is minus 1. And 1 minus 0 is 1. So I think it's easiest if you work through how the model predicts the outcome for each group, because then you know how it predicts the differences as literally subtracting those quantities from each other. Once you know how the model predicts the mean, you're home free. The differences fall out as subtraction. So things that you would have to change in order to use this. What model you're pulling from. The values in here correspond to what you're trying to predict and the result that you're saving this to. So I'm trying to come up with a naming system that is consistent. So for instance, like my model results, I always start with the word model, and then what is in the model? Oh, this is working class, so I called it model class. And then now I'm asking for predictions, so I put pred in front of it to differentiate that. So class is sort of the name for everything I'm doing with respect to this analysis. And then one more set of saves so that I can get confidence intervals. So it's like a nesting doll sort of thing that it ends up with when all is said and done. Most of this doesn't need to be changed though, just the names and the values. Okay, I know that's a lot. Questions? So let me back up and ask a question of you. When do I need to do any of this? How would you know that you need to go to the trouble to do all this as opposed to just running the model and hoping for the best?
You stated that we don't get any comparison between two categories here, the middle and upper class. But again, I'm coming back to the question, why do we need to go through all of that if we can visually do the comparison?
So the answer given was, why would we need to do this? Well, because I don't know what middle versus upper is, because that's not directly given by the model. But then he turned it back on me. Why can't I just do math? So I know what the answer is. I know that if I take the difference of these two numbers, then I know how middle differs from upper. But do I know if that difference is significant? Nope. The reason to ask for it to make the program do the linear combinations is to get the standard error that goes with the result. Yep, standard errors is why. Now you can do the math yourself to make sure that you did the coding correctly. Like if you understand the logic of what you're asking for, you can get your calculator and be like, okay, I know the answer should be like 2 because it's this minus this. Now let me see if I did it right in R, that I should get that number correct. But R will also give you the standard error, and that's why we do it.
So, just a follow-up question. Is it possible to calculate the standard error doing just math as well?
Yes, but the formula is more complex, and you would have to make sure that you carried forth enough significant digits so that the result wasn't subject to rounding error. So one of the things that's tricky is that different programs print this to different levels of precision. So if you're just pulling numbers out of your output, you will not get as precise of a result as if it's internally doing the computations for you. But yes, in theory, you can do anything with the formula if you're willing to. But my general question, when do you need to do this stuff, is when you need a standard error for something that is not directly given by the model. So the predicted mean for somebody who's not the reference group, any mean differences for not the reference group, anytime that you need a linear combination of betas to answer a question, then you got to go ask for it to do the math for you. All right. Other questions so far? So when all is said and done, you will end up with a table that looks like this. This is out of SAS, but the one from R will look quite similar. Stata listed as separate lines of output. It's a lot more voluminous, which is why I show the SAS output, because it's easier to summarize. So these are the three means. So this is the result of adding together the intercept plus the slope for how middle differs from low. There's my 22. This is the result of the intercept plus the slope for how upper differs from middle. That's my 24. Here are the numbers themselves, actually. So 13 plus 8.8 is 22. 13 plus 10.98 is 24. And 22 versus 24 is the 2. So the upper group is higher relative to the middle group by 2.13. However, is that a significant difference? Is that difference of how the upper differs from middle significant by alpha of 0.05? Thumbs up for significant, thumbs down. Yeah, this is a thumbs down. P-value is right here. Well, 2 is a lot. Why isn't that significant? Well, look at the standard error. Standard error is bigger than the slope. That's not good. That's SAS telling you, yeah, I have no idea what this difference really should be. The obtained difference of 2 is 0.7 standard errors away from the null hypothesis. An obtained difference of 2 or greater would happen 48% of the time if the true slope were 0. So a slope of 2 is noise, essentially. It's not different than expected inconsistency, because expected inconsistency is 3. So this is why we go to the trouble to ask the program to do the math for us, is to get the standard error and the hypothesis test that goes with it. Okay. Questions? Or any of that you want to hear again? So other things the output has not yet given us that we might want to know. Effect size. Remember effect size? A little bit? Shall we talk about effect size? The concept of effect size is exactly what the words you would think they mean, the size of an effect. The key is putting it into some kind of standardized metric where based on that number, people will be like, oh yeah, I know what that is. So a correlation is an effect size metric where no relationship between two variables is zero. A perfect relationship where as one goes up, the other is certain to go up is a 1. And as one goes up, the other is certain to go down is a -1. That's correlation. When we're talking about categories and differences between categories, though, correlation is less useful than another type of effect size, which is the standardized mean difference. So I want to show you how to get both of those things out of the output. So we're going to get R's and we're going to get D's. D's are differences between groups in standard deviation units, and R's are in a correlation metric. Now, do you remember in the end of your homework, for those of you who just finished homework 2, I asked you to compute a D in one of the questions. And the wording said, like, literally compute this. Like, this is the one time I want you to get a calculator out and find a D. And to get the correct answer, you had to find the t-test statistic, for instance, like this, that goes with it, multiply it by 2, and divide by the square root of denominator degrees of freedom. I gave you a formula. And you are able to do that just fine, but that's not ideal. So looking at the number in the output and taking that number and plugging it into a calculator is not ideal for a couple of reasons. If the number changes, you'd have to redo your work, so it's more work for you. And also because the level that it prints to is not as precise as the number is stored. So SAS told me the t is 3.67. That's rounded to the nearest hundredth. So it's imprecise when you're working with summarized output. A better strategy is to ask it to access the number that it has stored and do the math on that stored number in the same way that we did for the linear combinations. So I want to show you how to do that in each of the programs. So first up, in SAS, we'll go in order here. This command right here, that's new. ODS Output stands for Output Delivery System. It is a way that you can take the result tables and save them as SAS datasets so that you can do math on them. It's what happens in R already. So what I am asking for is this table of results, which SAS has labeled as estimates. Within the SAS documentation, you can access what it has named things so that you can communicate, is being saved as a new data set. The data set is going into the work library, and the name of the new data set is class estimates. So this piece of output right here has been converted to a SAS data set. So it has the true values of all of these things, not just to 2 decimal places, but to as many as it stores inside there. So to use this, you would keep estimates. The only thing you'd need to change is the name of the data set. You can call it class estimates, but if you don't have class in your model, then that might be confusing. You can name it whatever you want. Okay. So then the SAS code to do that, I am going to then go into that data set and do stuff to it. So I'm on page 5. So data work.class estimates set.class estimates, meaning I'm going to go into the data set and save it as itself when I'm done. The first line here gets rid of the rows that are for predicted outcomes, because we don't need effect sizes for predicted outcomes. We only need them for slopes. So index is a function that finds words in a string variable. So basically, if there are words in there that start with predicted, so in the SAS code, I think I had shortened it, but yeah, pred income is what it says, then delete those rows. Then otherwise, I'm computing a D and I'm computing an R using the conversion formulas that are in the slides. So T value is the name of the internal column that has this information. So I don't have to type the T in it. It knows what it was. The only thing I have to type in is denominator degrees of freedom, which is your sample size minus the number of fixed effects. So I have 3 fixed effects in my model, a sample size of 734, and that gives me 731 as a leftover. And then R is T over that thing as a denominator, the square root of T squared plus denominator degrees of freedom instead. And those formulas are in here, somewhere, here, side 21. That's where those came from. We haven't gotten to that slide yet. And so then I'm asking it to print that little data set, and the 2 columns that I added are on the end. So now I have effect sizes in a D metric for standardized mean difference, as well as in an R metric for correlation, that tell me in a more absolute way how large of an effect these are. Not just whether it's significant, which is a function of both effect size and sample size, but how big it is in an absolute way. So my slope of 8.8 is significant. It corresponds to a D of 0.65, meaning that the low and middle groups differ from each other by 0.65 standard deviations. That corresponds to an R of 0.3, so a positive correlation of sort of medium size. The slope of 10 corresponds to actually a smaller D, because the standard error is much greater for that slope, and a smaller R. And then the last one here, the slope of 2, that had a huge standard error, corresponds to a very tiny effect size. So these are additional pieces of information that you would want to report, in addition to whether or not your slope is significant. How big is it in an effect size metric? In the results section that follows this, I have sentences that try to put all of those concepts together. So for instance, this sentence right here, relative to lower class respondents, annual income was significantly higher for middle class respondents. Then I have the difference as the slope, the standard error of the difference, and then an effect size for the difference. And relative to upper class, there's their difference, the standard error of the difference, and the D effect size. And then the last one, that's a linear combination of middle versus upper. However, upper did not differ significantly from middle class. Here's by how much, here's the standard error for how much, and then the effect size follows. So you kind of put them together. What happened? Is it significant? And how big of an effect was it? Okay. So again, this part of it is accessing stored results to convert the results to effect sizes, so that you don't have to type the numbers in to your calculator. The same thing in Stata relies on accessing the results after each individual LINCOM statement. I couldn't figure out a better way to do it, but this way works. So for those of you who are using Stata, after each LINCOM, that's going to give you a slope. Paste this in and don't change a thing. It will work exactly as it is. because all of the pieces are stored from the analysis for you. So it's accessing the estimate, the standard error, and the formula is then computing the t for you. Degrees of freedom is already stored by the thing, so you don't have to change that either. So again, for those of you using Stata, paste those two lines after any lincom that you want an effect size for, and it shall appear. It's accessing the stored results for you to get the things that we need. So I have 3 sets of these that are identical because each time it is accessing a different result given by the lincoms that are before each. Likewise, those of you using R, the only thing you have to change is the name of the object. So the name of the model from the linear model command and the name of the saved output from the GLHT. The rest of it works because it's accessing objects in R that are within each of those saved pieces. Do you remember, like, at the beginning of the class when I told you that find and replace was your new best friend? Control F or Command F for Mac users. So when I give you these sorts of things to start with, find and replace, because it will find all the spots where it's referred to and change the name for you. It's not cheating, I swear. It's efficiency. So most of my example files are built so that a few find and replaces later, you have code that should work. And all 3 packages have a find and replace function. It's Control H to do find and replace in SAS and in Stata, and I think it's Control F that opens up the thing in RStudio. So that will save you in these sorts of instances. All right, 310. So we haven't talked about all the output yet. We've only talked about the solution for fixed effects. We'll get to talk about the table here next time, it looks like. So, big picture. What is all of this for? Predicting. So this process is relevant whenever you want to predict a quantitative outcome from a categorical predictor. That's what this is, like big picture. Step 1, create new predictors that are zeros and ones so that you can represent each group relative to another group as a specific slope. Step 2, put the new slopes in the model. Step 3, figure out what else you want to know that the model doesn't tell you directly. Step 4, get effect sizes for everything that you want to know about. There we go. So in Unit 2 and in Homework 2, you got a chance to practice how you would answer a research question about the linear effect of a quantitative predictor in predicting a quantitative outcome, as well as a binary predictor of a quantitative outcome. Now we're adding to our toolkit, how about if I had a categorical predictor of a quantitative outcome? This is what we do. Okay, questions? 4 steps again to answer a research question about how a categorical predictor is related to a quantitative outcome. Step 1, make the predictor variables. You can't put in the grouping variable of 1, 2, 3 directly because it will try to put a slope through 1, 2, 3, and these aren't numbers. So we need to make number of groups minus 1 new predictor variables. That's step 1. Step 2, put those new predictors in the model. See what happens. Step 3, realize what you don't know yet that you want to know. So in our example, I directly get to know how the middle group differs from the low group and how the upper group differs from the low group. I don't know how middle and upper differ, though. But I can find out by doing these sorts of linear combination statements. So GL, HT, and R, lincom in Stata, and estimate in SAS. That's step 3. Step 4, compute effect sizes for everything you care about reporting. Because it's not enough to say if it's significant. Effect size is imperative. And the optimal way to compute effect sizes is using the saved results, making it do the math for you so that the results are as precise as possible. There. Anything else before we call it a day? Okay, well, it's Tuesday, even though it feels like it should be Friday by now. It's not, which means I say thank you for being here. See you Thursday. Let me know if you need anything. You have nothing to do right now. I'll let you know when that changes. So, bye, folks. Thanks for being here.